Okay, I want to show how to do the following problem in Sage. So we've got this problem from Anton's book, page 66, number 15, that we also did in class. It says, determine the conditions on B1, B2, and B3 that make the following system of equations consistent. Okay, so we have some system of equations, and there is some condition, apparently, that B1, B2, and B3 have to satisfy in order for this system to have a solution. Okay, and so the way I first thought about doing this is, okay, well, Sage can work with variables, so introduce B1, B2, and B3 as variables like so. And okay, so these are the variables. And then turn the system of equations into the augmented matrix A. So A is equal to the matrix, and SR stands for symbolic ring. That's the ring, and a ring is just where you can add, subtract, multiply, and so forth. Not necessarily divide, but anyway. In the symbolic ring, there's this B1, B2, and B3. Okay, then we want to construct a 3 by 4 matrix because that's what the dimensions of this, the augmented system, or augmented matrix associated to the system is. And then the entries are going to be 1, negative 2, 5, B1, because the first equation is 1x1 minus 2, then there's a 5 in front of the x3, and then a B1 on the side here. And then follow that with 4, negative 5, 8, B2. Again, that's the second row, or second equation, 4, negative 5, 8, B2, and so on for the third row. Okay, so then we enter that, and so this is our matrix. And so I was going to then do, or then what I plan on doing and did, is compute the reduced row echelon form of this matrix A. And there's an equivalent command. It's a slightly different, but very much the same. And I didn't actually know the difference between before I made this video. Okay, so then compute the echelon form, and I get this thing, and similarly the reduced row echelon form, and I get the same answer. And I was surprised, but because this wasn't what this doesn't help us to solve the problem. And what happened is, you might say, well, I was wondering, where did all the B1, B2, B3, where did they go? Well, because they're not 0, Sage has been able to divide through by them in this symbolic ring, because you can divide by variables in the symbolic ring. And so at some point in the row reduction process, it divided through and got this pivot 1. And you might, yeah, and so, okay. So to fix this, well, actually just to kind of explain, this B1, what ring, where does it belong? It belongs to what's called the symbolic ring in Sage, basically the ring of all the variables you've introduced. And this ring contains 1 divided by B1. Basically, you can divide by the variables, or any combination of, polynomial combination of the variables, and they still lie in the symbolic ring. That's a little technical, you don't have to understand that. Okay, so here's how to fix the problem. And I had to Google this to find this solution. Okay, anyway, we cook up a new ring, and here's the definition of how to define a ring in Sage. So R, I'm going to call my ring R, and then it's going to have variables B1, B2, B3, and it's going to equal the polynomial ring generated by these variables. Now, this is very strange notation. I'm having a hard time getting used to it, but this is how to define things called rings in Sage. And what it is what R is then is the multivariable polynomial ring in B1, B2, and B3 over the field of rational numbers. So basically, this sounds complicated, but all it is polynomials in B1, B2, and B3. And the important point is you can't divide by B1 and still land in this ring R. Okay, so if I look at 1 over B1, if I try to divide by B1, and where does it lie? It lies not in this multivariable polynomial ring, but in the fraction field. In other words, the fraction field is where you're allowed to divide. This is something you'll learn in a later course, namely abstract algebra, so don't worry about it right now. So now let's use the same command to construct this matrix A, but instead of the symbolic ring SR, let's use this ring R that I called R, but you can call it anything, you know. So I use this R. So the command is the exact same as before, but instead of SR for symbolic ring, so Sage understands that SR stands for symbolic ring. R doesn't stand for anything except once you define a specific ring, which I did here. So that's the only difference in this line here. So now we've got this matrix A that looks exactly the same as the matrix A that we had before. Exactly the same, but the only difference is that Sage is treating our new A as living in this ring R, where you can't divide by things involving these B1s, B2s, and B3s. Okay, and so now when I try apply the echelon form method to the A, I get what I want. And this is the answer essentially we got in class, is that the B's are still appear here. What happened when I'm not working in the string R, but instead of the symbolic ring where I can divide, the Sage continues this process, and then of row reduction, and then divides through by this thing, negative B1 plus B2 plus B3, to turn it into a 1, and then use that pivot 1 to turn these things above it into a 0. And so that's how you get this answer it was giving earlier when I did the echelon form applied to A. It's 1 and then the 0 and the 0. But we can't in general divide by 0. Like for example, suppose B1, B2, B3 are numbers where somehow they add up to 0. If you have a negative, take a negative on the B1, and then this thing will be a 0, and that's when you'll get a consistent solution. And so that's the condition on the B1, B2, and B3, is that because this third row, or I guess row 2 in Sage's indexing, this last row is 0, 0, 0 equals this thing. So we have to have, in order for there to be any possible solution, we have to have 0 equals negative B1 plus B2 plus B3. So that's the answer. And then just to be a little bit more thorough, well, what are the solutions? Again, this problem is asking just for this condition, for there to be solutions. That's what it means to be consistent, a system of equations to be consistent. It means that there is at least one solution. There could be more. It doesn't have to be exactly one. Okay, and so to find the other solutions, or all solutions, let's look at the first row. The first row says x1 plus 0x2 minus 3x3 equals this thing here. And so solving that for x1, I get x1 equals this negative 5/3 and so on, plus 3x3. So what I've done is taken this negative 3x3, there's an equal sign between, so this is the augmented matrix. And so that's why I shifted this over to, and it became positive 3x3, and that's what x1 is going to equal. Then similarly, x2 is going to equal this thing here, plus 4x3. This minus 4x3 turned into a plus 4x3 when I moved it to the other side. And then x3 can be anything. That's what's called a free variable. Okay.